So far, we have learned numbers of scheduling algorithms, such as first come, first serve, shortest job first, priority scheduling, and round robin. Today, we are going to learn some more complicated scheduling algorithm, which will use the scheduling algorithms we have mentioned in the previous slides as a building block. The first one is called multi-level queue scheduling algorithm. The basic idea of this scheduling algorithm is that instead of having a single ready queue, in this scheduling algorithm, we partition the ready queue into a separate queues. For example, we can partition the ready queue into two sub-queues. One is called foreground, the other one is called background queue. We can put all the interactive processes in the foreground queue, and all other remaining processes can be put into background queue. For example, the batch processes, which means the jobs that can be run without user interactions. Multi-level queue scheduling algorithm can provide numbers of useful features. The first feature is that process permanently in a given queue. So for example, if we put a process into a foreground queue, before this process finish its execution, it will keep in the foreground queue. The second feature is that each queue has its own scheduling algorithm, which means we can apply different scheduling algorithms to different queues. Following the previous example, we can apply round robin into foreground queue, since all the interactive processes are stored in the foreground queue. And the round robin scheduling algorithm can provide the best responsiveness. And also, we can apply first come, first serve scheduling algorithm to background queue, which store all the batch processes. Beside the scheduling inside of each queue, we also need to do scheduling between queues to guarantee all the processes can get a chance to be executed onto the CPU. One way to do that is called fixed priority scheduling. For this way, we assign fixed priority to each queue. For example, if we assign higher priority to foreground queue, all the processes in foreground queue can be put onto the CPU first. Then background processes can start to be executed. However, since this solution belongs to priority scheduling, so the starvation problem may be happened. For example, if the interactive processes continually join in the foreground queue, the processes in the background queue will wait forever. But as we already mentioned that the aging solution can solve the starvation problem. Another way to schedule the queue is through time slice, so which means that each queue can get a certain amount of CPU time to do the execution. For example, we can assign 80% of time CPU time to foreground queue with a round robin, and 20% of CPU time to background queue in first come, first serve scheduling algorithm. Next, let's look at another scheduling algorithm, which is the most complex scheduling algorithm we have ever designed, which is called multi-level feedback queue scheduling. You may have to remember that whenever we refer the most complicated scheduling algorithm, actually we are talking about the multi-level feedback queue scheduling algorithm. Different from the multi-level queue scheduling algorithm we just mentioned, so each process will be put into fixed queue. For multi-level feedback queue scheduling, each process can move among different queues. Actually, aging can be implemented through this way. For example, when the process in a lower priority queue for a very long time, according to the time, this process can be moved to a queue with a higher priority to address the starvation problem. And also, actually, multi-level feedback queue scheduler is just a framework, so we need to further decide the details of each part. For example, we need to decide how many queues we need in this scheduling algorithm. And also, we need to specify the scheduling algorithm for each queue to schedule the processes inside of each queue. And then we also need to determine the method that when to upgrade or demote a process from one queue to another. And also determine a method that when a process needs a service, so which queue the request process will enter. In this slide, we will further explain multi-level feedback queue scheduling with an example. In this example, we have three queues, which are Q0, Q1, and Q2. For Q0, we apply round-robin scheduling algorithm to it with time quantum equals to 8. For Q1, similar as a Q0, it will use a round-robin to schedule the processes with time quantum equals to 16. The last queue, Q2, will apply first come first serve scheduling algorithm. And also, we need to design the rule that when a process arrives the system, which queue should we put this process to, and how to move the process among different queues. When a new process arrives the system, it will be directly put into Q0. Whenever this process is put onto the CPU, it can be executed on the CPU for 8 milliseconds. If the process finishes the execution, it will be removed from the system. Otherwise, it will be put onto Q1 and receive additional 16 milliseconds of time quantum. However, if the process still cannot finish its job, it will be put into Q2 with first come first serve scheduling algorithm. From this example, we can see that for all the newly coming processes, they can get the best responsiveness because all the newly coming processes are put into the Q0 first. And also, for the process whose CPU burst time is less than or equal to 8, so they can be finished very fast in the system. For all the process whose CPU burst time is less than or equal to 24, which means 8 plus 16, they can be finished relatively fast, even though a little bit slower than the previous processes group in Q0. However, for the processes need longer CPU burst time greater than 24 milliseconds, so eventually they will sync to Q2, which is with the lowest priority compared to the other two queues. But here we can apply aging solution to avoid the starvation problem. For example, when the process is inside the Q2 for a long time, which already exceed the threshold, so we can move this process to Q1 or even Q0 to make this process get a higher chance to be executed onto the CPU to avoid starvation problem. Therefore, you can see that so we can move the processes to different queue by aging.